Hello students. In 11th standard we have studied the combination of resistors. In my previous lecture we have studied capacitor and capacitance. Now today we are going to study combination of capacitors. And first combination is capacitors in series. So for that, consider three capacitors having capacities C1, C2 and C3 are connected one after the another in the form of a continuous chain. That means second plate of first capacitor is connected to first plate of the second capacitor, second plate of second capacitor is connected to the first plate of the third capacitor, and so on. And this combination is connected to a battery along with plug key, and this arrangement is connected to the ground. In this case, when number of resistors are connected one after the other in the form of continuous chain, and when PD is applied, or this combination called as series combination is connected to a battery having EMF E, then as these three capacitors having capacitance C1, C2, C3 are connected in series, the potential difference across C1 is V1, potential difference across C2 is V2, potential difference across C3 is V3. But the charge on each capacitor is same, which is of magnitude plus Q. So in this case, when number of capacitors are connected in parallel, the potential difference across the series combination, that is V, is equal to the sum of potential difference across the three capacitors. Again, by the definition of capacity of capacitance, C is equal to Q by V. We write V is equal to Q by C. And by using this formula, we write the formulas for V1, V2 and V3. So V1 is equal to Q by C1, V2 is equal to Q by C2, and V3 is equal to Q by C3. Now these values of V1, V2 and V3 are substituted in equation number 1, then we get V is equal to Q by C1 plus Q by C2 plus Q by C3. So this is equation number 3. And V is equal to, we write here, Q is common into bracket 1 upon C1 plus 1 upon C2 plus 1 upon C3, and this is equation number 4. Now, if this series combination of number of capacitors is replaced by single capacitor, that means if Cs is equivalent capacitance of series combination, then this diagram becomes, instead of all the three capacitors in series, we have taken only single capacitor and whose equivalent capacitance is Cs. So this is capacitance having capacitance Cs. Now, in this case, again we write the expression. So, across this equivalent capacitance of series combination, again potential difference is V, and therefore we write V is equal to charge on the capacitor is Q and divided by Cs. Say this is equation number 5. And if we compare the two equations, equation number 4 and equation number 5, we will find that Q divided by Cs equal to Q into bracket 1 by C1 plus 1 by C2 plus 1 by C3, and therefore we get 1 upon Cs is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. So this is the expression for equivalent capacitance when three capacitors are connected in series. If n capacitors are connected in series, then we write 1 upon Cs is equal to 1 upon C1 plus 1 upon C2 plus dash 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 plus 1 upon Cn. So from the expression number 6, we say that the reciprocal of equivalent capacitance, that is 1 by Cs, the reciprocal of equivalent capacitance in series combination is equal to sum of reciprocal of individual capacitance. So 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3, and the equivalent capacitance in series combination is given, which is the reciprocal of equivalent capacitance is equal to sum of reciprocals of the individual capacitance. Now, in case of series combination, if only two capacitors are connected, so suppose only two capacitors are connected across a battery and whose capacitance are C1 and C2, then we write, so two capacitors are connected to a battery, then in this case the equivalent capacitance is given by, we have already seen 1 upon Cs is equal to 1 upon C1 plus 1 upon C2. If n capacitors are connected, then plus 1 upon and so on. And as the two capacitors are connected in series, then by taking the LCM, we can direct write the formula equivalent capacitance in series combination, that is C1 is equal to C1 into C2 divided by C1 plus C2. That means equivalent capacitance for two capacitors connected in series is equal to multiplication divided by addition of capacity of two capacitors connected in series. So, when capacitors are connected in series, we have observed that the charge on each capacitor is same, but potential difference across each capacitor is different. And finally we have derived the formula 1 upon Cs is equal to 1 upon C1 plus 1 upon C2 plus dash 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 plus 1 upon Cn if n capacitors having capacitance C1, C2 are connected in series. Now, the second combination of capacitor is capacitors in parallel. In this case, if number of capacitors are connected one across the another, or the number of capacitors are connected between two common points. Suppose that there are three capacitors having capacity or capacitance C1, C2 and C3. And these three capacitors are connected between two common points. That means first plate of each capacitor is connected to one terminal and second plate of each capacitor is connected to the another terminal, and between these 2 points we connect a battery. So a battery is connected between points A and B. So this combination is called capacitors in parallel. So capacitors in parallel means when number of capacitors are connected one across the other between two common points A and B. And in this case, the potential difference across this parallel combination or PD across each capacitor C1, C2, C3 is same, but charges are different according to their capacity. So suppose that on C1 the charges are plus Q1 minus Q1, charges on C2 are plus Q2 minus Q2, charges on C3 plus Q3 and minus Q3. So in parallel combination, PD across each capacitor is same, which is V, but charges on each capacitors are different according to their capacities. Now, in this case, when number of capacitors are connected in parallel, here for simplicity we have considered 3 capacitors connected in parallel, then the total charge supplied by the battery or the cell, which is equal to the sum of the charges on the 3 capacitors. So charge supplied by the cell is equal to Q1 plus Q2 plus Q3. That means charge on capacitor C1 plus charge on capacitor C2 plus charge on capacitor C3. Say this is equation number 1. Again, by the definition of capacity of a conductor or capacitance of a capacitor, C is equal to Q by V, and therefore we write Q is equal to C into V. And by using this expression Q is equal to C into V, we can write expressions for Q1 equal to C1 into PD is same, that is V. Q2 is equal to C2 into potential difference is again V, and Q3 which is equal to C3 into potential difference D. And if these values of Q1, Q2, Q3 are substituted in equation number 1, we will get Q is equal to Q1, that means C1 into V, plus Q2 C2 into V, plus Q3 which is C3 into V. And in this expression Q is equal to V is common, into bracket we say that C1 plus C2 plus C3. Let us suppose that this equation number 2. Again, if Cp is equivalent or resultant capacitance of parallel combination, then we write, or this diagram becomes a parallel combination is replaced by a single capacitor and across which a battery is connected, and in this case the equivalent capacitance of parallel combination is Cp, and PD across this equivalent capacitance is V. Charges on the plates of the capacitor are of magnitude Q, and then we write for this equivalent circuit again charge Q is equal to Cp into V. So this is equation number 3. Now if we equate equation number 2 and equation number 3, we will get Cp into V is equal to V into bracket C1 plus C2 plus C3, and this V gets cancels, and therefore we get Cp is equal to C1 plus C2 plus C3. Say this equation number 4. So when 3 capacitors are connected in parallel, then the equivalent capacitance of parallel combination is Cp and is equal to the sum of capacitance of individual capacitor. And again, if there are n number of capacitors are connected in parallel, then we can write equivalent capacitance of n capacitors in parallel, Cp is equal to C1 plus C2 plus dash 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 plus Cn. So this is equation number 5. So in parallel combination, when capacitors are connected in parallel, that means they are connected one across the other, or they are connected between 2 common points, so that first plate of each capacitor is connected to one point and second plate of each capacitor is connected to another point. Then in this case the potential difference across each capacitor is same, and the charge is different according to the capacity of the given individual capacitor. And finally we have got the expression, the equivalent capacitance or resultant capacitance when number of capacitors are connected in parallel is equal to the sum of capacitance of individual capacitors in parallel combination. So, in today's lecture, we have discussed the combination of capacitor, and the combination may be series combination or it may be parallel combination of capacitors. But sometimes it is required in an electrical circuit to connect some capacitors in series and some capacitors in parallel. That means in some electrical circuit we have to use combination of series and parallel capacitors. Now, so next article is energy of a charged capacitor. And in order to charge a capacitor, this capacitor is connected to a DC source such as battery. Now, when this capacitor is connected to a source such as battery, then charges are deposited on the plates of the capacitor. So, when charges are deposited on the capacitor, the plate 1 of this capacitor acquires a positive charge. And in order to again deposit positive charge on the plates of the capacitor, the already deposited charge which are positive, and we are going to deposit again the charge which are also positive, they repel each other. That means there is a force of repulsion between the two charges, and we have to work against this electrostatic force of repulsion. Now suppose that at some instant or while charging the capacitor, the charge on capacitor is small q, and due to this small charge q, PD across the capacitor is say V volt. So this is the situation which is intermediate between the capacitor is being charged fully. So at some instant of time during the charging of capacitor, if charge on the capacitor is small q, and due to this charge small q, if the potential is small v, then we write the capacity of the capacitor C is equal to q by small v, or we write q is equal to C into V. Or we may write third form, V is equal to Q by C. So, while charging the capacitor, after some instant of time, due to charge small q on the plates of the capacitor, the electric potential between the plates of the capacitor is V, which is equal to Q by C. So this is equation number 1. Now, if a charge plus dq is to be deposited on plates of the capacitor, then as already the charge on the plates of the capacitor is small q, and again we have to deposit a charge which is equal to plus q on the plates of the capacitor, and therefore there is a force of repulsion between the charge plus dq and this charge already deposited, which is plus q. And therefore, in order to deposit charge plus dq against the force of repulsion, a small work is to be done, which is dw. And work done is given by formula dw is equal to V into dq. Say this is equation number 2. And this equation is obtained from the electric potential V is equal to work upon charge. So by using this expression, electric potential is nothing but work done in bringing unit positive charge from infinity to given point against the direction of electric intensity. So work done in bringing a charge plus dq against the force of repulsion is given by equation number 2. And therefore, to charge a capacitor fully, that is, capital Q is the total charge on the plates of the capacitor, then total work done is given by total work done W is equal to integration dW limits from 0 to capital Q. And therefore, the integration dW is equal to integration from 0 to capital Q V into dQ. So this is equation number 3. And from equation number 1, the equation number 3 becomes total work done, which is equal to integration from 0 to capital Q V into dQ. Value of V is Q by C, therefore Q by C into dQ. So this is equation number 4. And the total work done, W is equal to, we write here, common is taken or constant term is taken, which is 1 by C, integration from 0 to capital Q, Q into dQ. And this total work done is equal to 1 by C into bracket integration of Q into dQ is Q square divided by 2, and limits are taken from 0 to capital Q. If the limits are substituted in this equation, the work done is given by total work done, W is equal to 1 by C into capital Q square divided by 2, or we write this expression as 1 by 2 Q square divided by C. Now this total work done is stored between the two plates of the capacitor, or this work done is stored in the form of potential energy in the medium present between two plates of the capacitor, and therefore we write the energy of a charged capacitor is nothing but total work done, which is equal to 1 by 2 into Q square divided by C. So this is the one of the form of energy stored by a charged capacitor, and say this is as equation number 5. So from equation 5 we have got the relation 1 by 2 into Q square divided by C. Again we will find the different forms of the energy stored by a capacitor, and the different forms can be obtained by using the equation C is equal to Q by V. So as we know that C is equal to Q by V, and from this equation Q is equal to C into V. And if the value of Q equal to C into V is substituted in equation number 5 for energy stored in the capacitor, then energy is equal to 1 by 2, value of Q is C into V, square is C square, V square divided by C. So this one C gets cancels with this one C. So energy is equal to 1 by 2 CV square. Say this is equation number 6. So this is another form of energy stored by a charged capacitor. Again, from formula C is equal to Q by V, and if the value of C is again substituted in the equation number 5, we will get E is equal to 1 by 2 Q square divided by C. The value of C is Q by V, and this comes out to be E is equal to 1 by 1 Q gets cancels with this 1 Q. So E is equal to Q 1 by 2 Q into V. Say this is expression number 7. So there are three different forms of energy stored by the charged capacitor. One is E is equal to 1 by 2 Q square by C. Second one is E is equal to 1 by 2 CV square. And third one is E is equal to 1 by 2 Q into V. Then from equation number 7, if we concentrate on equation number 7 for energy stored by the capacitor, which is E is equal to 1 by 2 into QV. Then while charging the capacitor, we have connected the capacitor to a DC source such as battery, and when the capacitor is connected to a battery, it will supply the electrical charges. And the energy supplied by the battery or the source is equal to Q into V. But expression for energy is obtained which is half of Q into V. Then the energy supplied by the battery is Q into V, but energy stored by the capacitor is half into QV. Then where is the half QV energy supplied by the battery or cell goes? Then the answer is the half QV energy supplied by the battery is lost in producing heat when this capacitor is connected by the conductor, that is metallic conductors, and also due to loss of energy inside the cell. So this is the important point regarding the energy stored by a charged capacitor. Dear students, we have learned about the energy stored by a charged capacitor. And in this case, we have derived three different formulas. One is energy stored, which is equal to 1 by 2 CV square. Now, as this capacitor stores the energy in its electric field, therefore, the energy density of electric field is equal to, so energy density per unit volume is given by du by dv. So du by dv is the energy stored in the electric field, that means energy density, and therefore the energy density of the medium, which is equal to du by dv, say which is equal to U. So energy density U is equal to, as we know that the energy stored by the capacitor is 1 by 2 CV square. So as U is equal to 1 by 2 CV square, for parallel plate capacitor, the value of C is equal to AK epsilon 0 divided by D. And again we know that E is equal to V by D, and hence V is equal to E into D. If these two values are substituted in the expression for this electrical energy, then we get this E is equal to 1 by 2 CV square is equal to 1 by 2, value of C is AK epsilon 0 divided by D into value of V is E into D, so E square divided by D square. Now in this formula, we know that this D and this D gets cancels with each other. Again, this area multiplied by this distance d. So area into d is volume, and therefore our formula becomes E is equal to 1 by 2 epsilon 0 k into A into d, which is volume, and into the term E square. And therefore we write energy per unit volume, which is also called as energy density of the electric field between the two plates of the capacitor, and it is equal to 1 by 2 epsilon 0 k E square. So this is the formula for energy density of electric field in the capacitor, which is 1 by 2 epsilon 0 k E square.